Next, we will welcome Dr. Rui Li. He is a tenured professor at the Deggendorf Institute of Technology. He received his PhD in nuclear engineering from Tokyo Institute of Technology. Dr. Li has many years of experience in the fields of computational fluid dynamics and supercomputing. He will review possible quantum algorithms and software for simulations of transport phenomena in computational physics as a concrete application. Dr. Li, the stage is yours.
Thank you. It is a pleasure to be here. So my name is Li, and I'm going to talk about the quantum software, taking the computational fluid dynamics as an example. So how can I go forward? Ooh. Green button?
The big green.
Oh, this big green. Okay, cool. Okay, so first I would like to basically make a very short introduction. What is computational fluid dynamics? Then show some basic or classical codes we have achieved so far, based on my experiences simulating reactor and other things, and also I turned to quantum tools and software. So basically, I would like to tell a story based on my own experiences, how I changed from traditional HPC, high performance computing, to quantum computing. I'm trying to do something, do the transition work. So then in the end, I would like to show some quantum computing from our research group in Deggendorf, showing using the Lattice-Boltzmann method. Then I will make some remarks. So basically, this is CFD. So CFD is kind of belongs to fluid dynamics, but without experiment. Basically, you use computer to simulate everything, as long as it's air, as long as it's flow. So basically, we are trying to simulate the so famous Navier-Stokes equations. With Navier-Stokes equations, we can, so if you smoke, probably you will ask yourself why your smoke is looking that way. So that is called turbulence. If you take a plane, you have turbulence. Every time you have to sit down there, fast yourself fast. What is turbulence? Turbulence is something, air movement in the sky. So this is difficult to understand. One has to use computer to simulate, make a lot of modeling. Then we probably get some result, like the weather per text, or some artist. This painting is from Van Gogh. He is trying also to say something turbulent, which is controlled by this equation, Okay, so then, for example, if we take the plane as the example, so the plane, the Airbus, the European company, French, Germany, so they are using a lot CFD simulation to simulate, to test their plane if it's work or safe enough. So this Airbus. So basically, those are simulations based on classical computation. Now, of course, we ask ourselves, what if we simulate those things with quantum computing? This is a big and specialized problem. I will try to answer in that way. So then come back to my background. So basically, I was doing almost 10 years nuclear safety research. Of course, you know, Germany is phasing out, but the European research, or French guys, the Belgian guys, they are doing still doing some nuclear. So if you want to keep this guy safe, you have to know how safe it is. Then the only way to to prove it is safe is doing simulation, numerical simulation. So basically, this is what was my work. So we are trying to using numerical simulation, using CFD to saying, okay, this reactor is going to be built called Mira, it's going to built in Belgium, it's going to be safe. We are trying to prove that. If it's not that safe, we have to give a number, how terrible it is or how good it is. So this can be done in computational fluid dynamics together with reactor physics. So basically, my work was like this. Then now I'm always asking myself, what if I can simulate this using quantum computer? Nowadays, impossible. That's a long way to go, but we would like to try. Okay, so basically is this. I would like to show if a nuclear explosion happens. So basically, you don't do the experiment, but you do the simulation. So if I suppose this works, yeah. So if you assume the nuclear is going to explode, yeah, a lot of energy, a lot of radioactive material is going to come out, then the only way to do it is doing simulation. So this is the simulation. We're using so-named mesh, so many mesh, and using Iran method, and we use the 3D simulation. But it's not so looks, yeah, like this. It's usually nuclear physicists simulated in this way. We make a lot of simulation, we make a lot of modeling, we make a lot of assumptions, which probably is not correct. But without those assumptions, we are not going to do it. Therefore, we are thinking, okay, probably quantum, since it's superpower, supercomputing, probably this can be done by quantum computer. So another way is, this is quite simple. If we see this simply water, collapse is so simple. Simply, if you have a tea, you have water, then we call it slosh. Come back, come back over. It's a so simple phenomena. Nowadays, people don't understand that clearly. Therefore, we do the analysis using also simulation, normal simulation, yeah, with supercomputing, with GPU, CPU, whatever you want to take. This can be done nowadays, but not so quick enough. So therefore, we would like to say, okay, since these two examples, yeah, we would like to ask, okay, probably we can do or try to do some thing with quantum computing, try to simulate. So basically, I quote this Susan Staplery, her words. So software is what, or software tool is what. So basically, you have to restructure. It's not translate. That's simple from German to Italian, or from Italian to German. It's a completely fundamental restructure to the algorithm, to the way of your thinking. So the more you look at the classical algorithm, you want to do really some concrete things like the CFD, simulating fluid, then you see, oh, it's too weird, it's too terrible. How can you do this? But we would like to try to do it. At least we would like to try. Okay, because quantum computer is the future. Okay, of course, everybody will know, since you are here, the quantum is kind of strange. So kind of strange has superposition, has this alignment, so it's not that easy compared to classical computer. So we have to translate all those things from the very deep point of view. Of course, quantum computing can be used everywhere, chemistry, finance, just mentioned, and so on and so forth. So then if we're talking about those tools, we have many tools apparently. We have the IBM, we have the Atos, we have the Intel. But if we have this qubits, if, as many of our said, we need at least, it means 5,000 physical qubits if you can really do something, So this is a roadmap from this year to, or apparently to now. So basically, this is the roadmap. If you really have the log gate qubit, then to physics qubit. So you have to done a lot. But before that, we can still do something. So this roadmap, the real machine, not everyone has the real machine. Therefore, there's a concept is the simulator. So we don't have to send every pilot to the plane. We have the simulator. Assuming it works in that way, we call it quantum software. Assuming quantum computer works that way, then probably we can do something already without a real quantum computer. So basically, this is quantum simulator software. So from the European, from the IBM, from Google, from Microsoft, in the end from Intel. So basically, this is the from 2000 to today. These are an overview of all the quantum tools and quantum software available on the market. You probably can try it. Most of them have access to everyone. Basically, you can try your problem. So this is what we are going to try. We are really asking ourselves, what if we try those tools? Simply use this tool to simulate not Airbus, not a nuclear reactor, but simply air flowing from A to B. So therefore, I'm going to show a case from our research group, which is really new. I believe has been done only by us. So basically, this means we are going to try those tools to simulate a very fundamental phenomena which is called convection. Convection basically means, if temperature here is high, here temperature is low, then the air will go from high to low. That's it. So this is simple case. As I said, before we simulate Airbus, nuclear reactor, we would like to try those tools to start with a very simple case. Very simple case, of course, we are not alone. Some people already done something. So basically, they are done in America. So Europe in this time is not in fluid dynamics field is not that quick enough. So basically, there's LBM. What I'm going to show, what is Lattice-Boltzmann method. Boltzmann apparently is a famous scientist. What is lattice? Then there are also the so-named final difference. Some people already tried to do something. And I would like to try what we have done in Europe. So basically, this is this. What is quantum Boltzmann method? So we name it as QLBM, so quantum Lattice-Boltzmann method. So if we see this, simply air from A to B. We have the Navier-Stokes equations, simply is air from A to B. Then we have the particle. Particle basically means moleculars. So from molecular to air. One is, not continuous, another is continuous. So basically, LBM is a method which really fits to fluid dynamics. So why we don't start with particle, why we don't start directly with Navier-Stokes, we call it macroscope, micro, but we start usually, this is the easiest way to start with the fluid dynamics. The easiest way is mesoscope. So in between, you kind of assume in a latex, in a box, those things, how it behaves. So this fits really well with quantum gates. So this is the reason why we pick up this method to start with our really simple case with quantum computing. So as I said. So basically, if we have to play with the gates, so this is our work, the chat flow from start to the end. We have to, as I said, classical 1D advection-diffusion. So the air is from hot to cold, very simple case. So we have to play for encoding, correlation, repropagation, and macro calculation, then end. So I will not going to show the details. I'm only want to show, we have done something. So then if we really implement those circuits using the tool I showed earlier, we try different kinds of companies tools, and in the end, we tried have this result, which in my opinion is really cool. So we have, in the end, we have this diffusion problem has been solved, basically using Intel quantum SDK. So most of the part are doing by Intel, was done by Intel quantum SDK, and we have this. Oh, can I go back? I don't know if I can play this movie. A red button. There are 3 movies I would like to play with. Go on, not. Okay, anyway. So basically, these are three wonderful movies. So basically, this is produced by, maybe I can try, by the way. Maybe I can try, give me 1 second. If there's, okay, anyway. So anyway, so there are 3 really results from the quantum tools. So basically, it's a really really simple example. But as we usually say, also the first march, the very 1,000 kilometers, even 1,000, begin with the first steps. So therefore, we would like to show in this case, to show, we are doing something in Deggendorf, and I have 2 minutes more. I would like to show something about our study program. I hope really young people or older people come to us to exchange with this program. We exchange with industry, with academia, and so on and so forth. And before doing that, I would like to say transport phenomena, like the Airbus doing, nuclear reactor is doing, is really difficult to simulate. But we would like to try it. So what we have to try is using Lattice-Boltzmann simulation method. We have done something which is validated with the experiment data. So purely 100% quantum result. So everybody talks, yeah, we have to do something, we have to deliver something. Then inside this study program. So if you would like to visit us in Deggendorf, so there are our study program head is also here, Helena Liebert is also here. So so this is the master study program, 3 years, 1.5, 3 semester, 1.5 years. In Deggendorf, totally in English, because quantum is really international. You have to everything taught in English, communicated in English in Deggendorf. And of course, you need some exam to come here. And we need B level, B2 level as English. And we are basically looking for bachelor student, graduate with computer science, physics, or technology engineering. And this is our contact information. I also bought some flyers here. If you want, you can take just for information for your friends, children, for your own children. Come to Deggendorf to work with us. And this is basically the module. So what the kids has to learn in here from the hardware design, software design, and system design. So system is really important. How do you keep those together? So and 80% also engineering interdisciplinary courses. One of our students is also here, by the way. And thank you so much for your attention. I think I keep it on time.
Thank you, Dr. Lee. It is a really nice study program. Are there any questions? Yes.
So thank you very much for your talk. So for your simulation that you did for the quantum Lattice-Boltzmann method, so what was the particular quantum advantage that you found? Was it time? Was it what did you discover?
Really?
I didn't get it. Maybe it was in the animations.
Yes. So basically, we are not in a step to saying quantum is quicker, is efficienter, is less time. No, we are still in a stage saying quantum can do. So you always have the steps. First, we want to say, okay, it works. Then we try to prove it probably works faster, probably works not faster. Could be also. This is the science, yes? But the first step is always we have to prove it works with quantum algorithm. So this real fluid dynamics problem works with quantum. This is the first thing we want to say. But you said how good it is or how bad it is next step. Maybe the next students are going to answer. But for the first one, we want to try to say it works. So I think for the other problem is also we are not in a stage saying, oh yeah, it's really good. No, at least in this area, not yet. But it works. This is the main thing.
There's another question.
Thank you. First of all, a great style of presenting. Thank you very much. Very enjoying. I was wonder from your point of view, seeing the hardware roadmap of all the hardware providers at the moment, that
yes.
they are starting to share only the amount of qubits, less about error correction and everything around it. How is this from your perspective as a kind of end user, seeing just the bigger numbers and they are starting to fight? For me, it's some kinds remind me on the fight on CPUs, AMD, Intel, who has more gigahertz at the beginning. How is your experience with going into this test, for example?
Oh, thank you. That's a really great and big question. Yeah, of course, the real machine has noise and everything, so many difficulties. So we are only play with, like you said, end user use the quantum software. But I think the basic information from this quantum software development is give us hope. So probably it's not perfect. It's not perfect yet, but give us hope. Probably after 20 years, it could be perfect. So then, in the meanwhile, we make our things ready. So when, let's say, in 20 years, 30 years, the noise problem has well be solved, cooling, everything is solved, then we are ready. Then it can be worked together. We don't have to wait. So if you wait for this guy ready, then it's wasting time in my point of view. Therefore, let's say this way. So those hardware give us hope. Therefore, we do this software thing. Then let's hope it works. I believe it works. So yeah, in this way. Before, so we simulate now the small area, small airflow. Hopefully, probably, I really hope in my life, the quantum simulator can simulate Airbus. I hope. Quantum computing can simulate Airbus.
Okay, thank you, Dr. Lee.
Thank you.